and hopefully is feeling well again. I'm going to take you on a short journey through Bayesian Magic Land. So, first of all, let me thank the organizers to invite me to talk here today, but maybe I'm not the perfect choice for standing here. The real perfect choice would have been Michael Gruber-Bauer, who was actually invited first, but as he left astronomy and got a real job in metrology, he's working at the company, so he wasn't available anymore, and the organizers asked me. So I'm not a real expert in Bayesian statistics when it comes to the sometimes really complicated mathematics that is behind it, but at least I can say I'm kind of an experienced user of Bayesian techniques. I started to use Bayesian analysis a long time ago when basically nobody else in asteroseismology was using it, and I hope I can tell you a few stories today. So what I'm going to talking about, we are now in the session probing stellar structure and evolution with asteroseismology. What does that mean? It often comes down that we have some observations of a star and we want to compare it to a model and to tweak the model that we actually can learn something about the stars, and in the best case we can even learn something about the physics behind that. A very popular path to do so is that we have, for example, a Kepler light curve. We compute the power spectrum of that light curve, and for a solar type oscillator we will immediately find that the oscillations that we are most interested in are superposed with different signals, with signals from other sources, for example granulation. So we have to find a way to disentangle the oscillations from the background signal. If we have done that, we get a clean spectrum where we can extract the mode parameters we're interested in. Then we have a list of frequencies, can produce shell diagrams, and finally we can compare these frequencies with frequencies from stellar models and hopefully learn something about physics. But along this path we will find a number of fitting problems. So we have to disentangle the spectrum, we have to fit our modes, and we have to compare the observations to the models. So what's the fitting problem? If you have some observations, you have to ask yourself two questions. What is the best model to reproduce these observations? If you once you decided for a model, you have to tune this model, you have to determine some parameters to reproduce the observations. That sounds easy, but it almost never actually is. So a good solution for a fitting problem is provided by probability theory. Probability theory basically builds up on two and only two very simple rules. First, the product rule, which means that you get the probability of a proposition A and B given a proposition C, and the sum rule, which tells you the probability of a proposition A or B or both given C. Why is probabilistic analysis always called Bayesian analysis? Simply because Thomas Bayes formulated his famous theorem, which simply follows from the product rule. So what are the facts behind this buzzword? Everybody in the room has for sure heard about Bayesian analysis, but I'm also quite confident that at least a fraction of you doesn't really understand what's actually meant by that. So Bayesian analysis provides you with a quantitative approach to solve a fitting problem, meaning that you can determine parameters and their uncertainties. Probability theory, if you correctly use the basis of the probability theory, so the product and sum rule, you will always get consistent and correctly normalized probabilities, which means that you can compare different models in a consistent way and subsequently also compare different physics. And a very nice trick of Bayesian analysis is called marginalization. What's behind that? Quite often you have the situation that you have a parameter in your model where you don't really know much about it. So the best, or the best way would be just to get rid of this parameter. But in a normal way, that's not easy doable. But thanks to a trick in the Bayesian analysis, you can integrate this parameter out. And that's what is called marginalization. So that's the basics behind that. Let us stop at the first stop along our path, which is the granulation background. That's the first fitting problem I'm going to talk about. So if you have a solar type oscillator, start with a convective envelope, like the sun as shown here, and you are interested in the oscillations, you will see that there's an additional signal which is due to granulation on the stellar surface. And the first one who modeled this signal was Harvey, using a quite simple Lorentzian profile to get rid of the signal, to get a handle on the signal. But it soon turned out that this simple model might not be the best one, and people started to modify the model, and a couple of years later we were in the situation that we had an entire zoo of Harvey models. But which one is the actual best model? Which one should we use? And that immediately calls for a Bayesian analysis. So how to pick the right model? The way we did it was using a standard tool of Bayesian analysis called multinest. It's a Bayesian nested sampling algorithm, which was developed a couple of years ago and which is nowadays the standard tool in particle physics and extragalactic research, but only find its way to asteroseismology only recently. So what does multinest? Multinest provides us, you plug in some model you want to fit to some observations, and the algorithm provides you with the probability distributions of the parameter for once, and it also gives you a global evidence for this model. And this evidence is correctly normalized, so you can immediately compare the evidence of a model to the evidence of another model. And that's what we did for our granulation models. So we have 4 different basic models. Each of them we were fitting 1 component and 2 components to the power spectra of various stars, and compared the model evidences, and immediately found that most of the models were completely ruled out by the model evidence. We were left with 2 models that basically shared the entire probability cake, but there was not enough evidence to pick one of these models to be the best one. However, it turned out that both models resulted in almost exactly the same parameter values. That's why we decided to go for the simpler model. So what have we learned about this exercise? Well, it told us that the original Harvey model is not really the best way to go. It also told us that it is extremely difficult sometimes to fit or to reliably fit the parameter alpha, which is simply the slope of the granulation signal, even with the 4 year long Kepler time series. And we also learned that the simple super Lorentzian profile works for all stars in our sample, in our Kepler sample, and gives reliable parameters. So thanks to that lesson, we could extract the granulation timescales and amplitudes in a much better way than this was done before, and could do actually some science with them. So the next stop along the path is peakbagging. What is peakbagging? It's frequency extraction. You have a power spectrum with some solar-like oscillations in it and want to determine the parameters of these modes. So the best way to do is to fit the Lorentzian profile to each single mode, which has 3 parameters. Sounds easy again, but it actually turns out that you have to fit all of your oscillation modes simultaneously, and you will immediately see that this builds up quite a lot of free parameters in your fitting process, which is not a good thing. I'm showing here a kind of famous example, one of the first solar type oscillator observed with CoRoT HD 49933, and it took us quite a while and at least 3 different publications to come up with a solution for the frequencies for this particular star. But things can get even more complicated if you include rotation. We have already heard that stars rotate, and as a consequence, non-radial modes are split up into different components, which adds at least 2 additional parameters for each of the split modes. So here I show an example of a red giant where we had to fit quite a number of dipole modes to get the individual rotational splittings and also the inclination angle. Over the years, there have been a number of algorithms developed using Bayesian techniques, but I would like to introduce one of my own. It's not finished yet. I'm again using a multi-nest, and the peakbagging tool I'm in charge of is designed to semi-automatically, it's not possible to do it fully automatically, peakbag the many, many stars that we now have available thanks to Kepler and CoRoT. It is designed to be as flexible as possible so that you can turn off, for example, rotation. You can combine different parameters, and it is also designed to do a multi-model analysis. So you plug in a number of different models and run them all, and finally compare the evidences of the model to see which of the model works best. In that context, I refer to the next talk given by Enrico, who also developed a Bayesian peakbagging algorithm for edge giants. Finally, we come to the good stuff, the grid modeling. So just to remember what is meant by asteroseismic model fitting, you have a star, you observe it, you come up with a power spectrum, you extract the frequencies, then you have models. You compute your models and compute the eigenfrequencies and compare them to the observations. That was usually done with the classical chi-square approach. So, as I said, you have a grid of models with eigenfrequencies, you have your observations, and then you just search your grid for one particular model where the differences between the observations and the model frequencies are smallest. And this best fitting model is a function of some fundamental parameters, radius, mass, effective temperature, but also the input physics. However, this classical approach comes with a number of problems. First of all, you need a mode identification. So you need to know which modes to compare. It doesn't make sense to compare theoretical radial modes with L equal 2 modes that you have observed. Quite often, you will find rotationally split modes, and you don't know a priori which M value they have. But there are more problems. So, of course, your grid resolution is finite. So you can't compute an infinite number of models, and this can really get deadly, for example, for bump modes. But you also have systematic errors in your models. We know that, for example, in a solar type oscillator, at the higher radial orders, the model frequencies deviate from the observations from where they actually should be. But we can't do nothing about that because we don't know the physics well enough to solve it. So let's now concentrate on this, what we call the surface effect. So as I said, due to the incorrect modeling of the outer layers of your models, you get systematic deviations between the frequencies that you actually compute and where they should be. A way to solve this problem is to include, for example, non-adiabatic effects. They about a third to a half of the deviation goes away if you include the radiative non-adiabatic effects, but there's still a surface effect left. So another clever idea was to look at frequency differences instead of the absolute frequencies, because the differences are not affected by the surface effect. However, whatever frequency combination or frequency difference you define, you will always lose some initial information. So the best way is still to use the absolute frequencies themselves. Hans Gerson and collaborators found that you can model this surface effect. So they came up with a simple model for the surface effect in the sun and simply scale this model to other stars. The downside of this approach is that you have to assume that the surface effect is always the same. It always scales from the sun, which you don't know. So given these problems, we came up with a less restrictive method using the advantages of Bayesian statistics. So if we formulate the chi-square mode in a chi-square method in a probabilistic sense, we can define the probability that a given mode is matched by the theoretical mode in this first probability, and using the product rule, we can compute a probability that an entire model matches the observations. And now we can introduce a frequency difference to these probabilities, which is shown here. So by simply adding another value, another parameter there, we actually treat the surface effect. Okay, but we don't know how big the surface effect is for a given star. But as I told you in the beginning, thanks to Bayesian magic, we can get rid of parameters we don't want. So simply by integrating the probabilities between some boundaries, very widely set boundaries. That might sound a bit strange, but it actually works. And if you're interested about the details, it's well proven in the paper cited down here. So we get a way to deal with the surface effect. So we can put the check mark there. What about mode identification and finite grid resolution? That's solved in a similar way. I'm not going to talk about that, but you can check it out in the paper. Okay, the first application of this new method was, of course, the sun. In helioseismology, we still have the problem that, or we still have a number of problems, one of which is the abundance problem. There were the abundances a long time ago, and helioseismology worked really fine, but then Asplund came up with some new abundances, and suddenly helioseismology didn't work anymore. Not completely, but there was a problem. So Michael Grubauer and David Gunter tried to get a hint on that, and they used this developed method, computed a whole bunch of models, 5 million models, using 3 different sets of abundances and also 2 sets of nuclear reaction rates, so actual different input physics, and compared this model to Bayesian frequencies of the sun. The results were, well, not that clear. They actually found that the frequencies alone did not provide enough evidence for any of these models. So the next step was to imply some prior information. We know the fundamental parameters of the sun to really good precision, so also the models should have the same fundamental parameters. Doing so, they found that the frequencies suddenly selected the revised abundances. But there was still a problem, because the best fit model now was too old, and they were not able to find a combination of whatsoever parameters where they can reproduce all of the informations we have from the sun. So that's the Bayesian evidence. That's a single number that tells you how good your model represents the observations. That's a probability at which you can directly compare for different models. So the better the evidence, the better the model. And if you have a difference in evidence, then you can say this is enough evidence that you can actually pick a particular model. So, okay, the conclusions of this exercise were that we still don't have a definite solar model, because the best fits we have right now are still too old and they don't reproduce all of the observations. So what does that mean? There has to be something fundamentally wrong with the models. However, there are also a few nice results. So contrary to the literature, helioseismology does not favor the traditional models. So in fact, the revised abundances are strongly favored when we add some prior knowledge to the analysis. And finally, also that the surface effect is not the problem here, which is a good thing. In the next step, we applied the method to a set of well-defined Kepler stars, 23 main sequence solar-type oscillator observed by Kepler, and there were lots of modeling efforts on these stars, summarized in these papers here. But in our own analysis, we actually measured the surface effect for the first time in a sample of stars and found some indication that the surface effect is correlated with the mixing length. So that brings me already to the end. My time is almost over. There would have been quite a lot of other nice results, but in a short talk you cannot present them all. That's why I leave you with a little ad for Bayesian analysis. Use the power of evidence. Thank you.
Questions? There are lots. I don't know who were first. We'll start with Jesper.
Well, I'll make some of a classical remark of mine. If you look at those solar models, they are all rejected with enormous evidence, all of them. Why should I believe one of them over another one when they're all rejected by an enormous amount of evidence? They are 100 sigma, on every data point.
No, they're not.
Yes, they are.
you almost perfectly fit the lower radial orders. The problem are the higher radial orders, just because of the surface effect. And this new method takes this surface effect into account. It allows for systematic deviation.
Let me maybe comment on that.
Yep.
Part of the discussion is because you very appropriately in this meeting is looking at the sun as a star. But if you include all the data we have on the sun, then the old abundances are preferred by a very large margin, looking at sound speed inversions. It's true, I can believe it, I haven't checked it, that you can do a better fit to the Bayesian data if you just just looking at the Bayesian data, you can get a better fit with the new abundances. Although certainly with an older age, that's been known for a long time. Just a second comment, if I may, and I have no question, don't worry. Matur et al. Actually did look at the amplitude of the surface effect and showed that it correlated with the large frequency separation. I don't know whether that means anything physically, because I agree that the surface correction doesn't mean much physically, but there's some evidence there that I want you to think about.
Yeah, Mike?
Yeah, on that line, I think that this is an incredibly powerful technique. You showed some very, very nice results, but I think Jan just highlighted, I think, one of the limitations, which is to say the Bayesian technique only knows about the things you put in, right? So at some level, if you don't put in the information from the higher order modes in the sun, if you don't put in the information on acoustic glitches, you're going to come up with one conclusion. If you do, you'll get a different one. And so one question then is if it's possible to do the same kind of analysis you just described, but one that incorporates a fuller set of solar data to see what you get then. In other words, if I were to put in more than low L, if I were to try to put in larger L, it may be computationally challenging, but could you do a Bayesian approach that included that?
Yeah, we have tried that because we wanted to treat the sun as a star. Because we wanted to have tools available we can use for Kepler data.
Okay, a quick question from over here.
On your diagram for the fit to solar models, right, when you said the evidence suggested, what meaning is the numbers on the vertical scale? What do they mean?
That's a logarithmic probability.
So none of them are probabilities.
Say again?
You can order them, but you can't say anything more than ordering.
The interesting information in these numbers are the differences and not the absolute values.
Well, that's what you're saying, but I think that's just ordering things, saying one is better than the other, but not how good they are, which is what we want to know.
Yeah, but how you can answer that?
Yeah, not by
Okay.
What does it mean, how good they are? They're good, they're worse?
I think we should move that discussion till later and move on to the next speaker. So let's thank Thomas again.